Alkanes are a fundamental class of organic compounds. They consist only of carbon and hydrogen atoms, all connected by single bonds. This makes them hydrocarbons. Alkanes are saturated hydrocarbons because they have the maximum number of hydrogen atoms bonded to each carbon atom. We encounter alkanes in our daily lives in various forms. They are the primary components of natural gas and petroleum. Methane, the simplest alkane, is used for fuel and heating. Propane and butane are also common alkanes, used as fuel in grills and lighters. Alkanes are relatively unreactive compared to other organic compounds. This stability makes them useful as solvents and lubricants. They are also important starting materials for the synthesis of a wide range of other organic compounds. Their simple structure and lack of functional groups make them ideal for studying basic chemical principles. Understanding the properties and reactions of alkanes is crucial for comprehending the vast and complex world of organic chemistry. From fuels to pharmaceuticals, alkanes and their derivatives play a vital role in countless industrial processes and everyday products. The synthesis of alkanes is a fundamental process in organic chemistry. There are several methods for creating these essential hydrocarbons. One common method is the hydrogenation of alkanes. Alkanes are hydrocarbons that contain a carbon-carbon double bond. Adding hydrogen to an alkene breaks the double bond, resulting in an alkane. This reaction typically requires a catalyst, such as platinum or palladium. Another important method is the Wurtz reaction. This reaction involves treating an alkyl halide with sodium metal in a dry ether solvent. Alkyl halides are alkanes with a halogen atom, such as chlorine or bromine, replacing one of the hydrogen atoms. The sodium metal reacts with the halogen atom, forming sodium halide. The remaining alkyl groups then combine to form a new alkane molecule. This reaction is particularly useful for synthesizing symmetrical alkanes, where the two alkyl groups are identical. In addition to these methods, alkanes can also be synthesized through the reduction of carbonyl compounds. Carbonyl compounds contain a carbon atom double bonded to an oxygen atom. Reducing agents such as lithium aluminum hydride or sodium borohydride can donate hydride ions to the carbonyl group, converting it to an alcohol. Further reduction of the alcohol then yields the corresponding alkane. To illustrate the methods of alkane synthesis, let's consider a few examples. For the hydrogenation of alkenes, imagine reacting ethene C2H4 with hydrogen gas H2 in the presence of a platinum catalyst. The double bond in ethene is broken and two hydrogen atoms are added, resulting in the formation of ethane C2H6. This process is widely used in industry to convert unsaturated fats to saturated fats, as in the production of margarine. Moving on to the Wurtz reaction, let's take the example of reacting methyl bromide, CH3Br, with sodium metal in dry ether. The sodium reacts with the bromine atom, forming sodium bromide, neighbor. The two methyl groups then combine to form ethane, C2H6. This reaction is a classic example of a coupling reaction, where two smaller molecules are joined to form a larger one. Finally, for the reduction of carbonyl compounds, consider the reaction of propanal, CH3CH2CHO, with lithium aluminum hydride, LiAlH4. The LiAlH4 donates a hydride ion to the carbonyl group, converting it to an alcohol, in this case propanol, CH3CH2CH2OH. Further reduction of propanol with LiAlH4 yields propane, C3H8. This reaction highlights the versatility of reducing agents in organic synthesis. Alkane synthesis is a cornerstone of organic chemistry. It underpins countless industrial processes and research endeavors. The ability to synthesize alkanes from readily available starting materials allows chemists to produce a vast array of compounds with diverse applications. For instance, alkanes are the primary components of fuels, lubricants, and polymers. Understanding the principles of alkane synthesis enables the development of new materials and technologies. It also allows for the optimization of existing processes, making them more efficient and environmentally friendly. From pharmaceuticals to plastics, the impact of alkane synthesis is far-reaching, shaping our modern world in countless ways.